Hello and welcome to this revision session on electromagnetic radiation, which is the topic in AQA A-level physics. So in today's revision session we're going to focus on answering examination questions on the A-level physics topic of electromagnetic radiation. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-level examination style questions, assess our understanding on A-level physics and understand what topics we need to improve upon for A-level physics. So how do we prepare for this revision session? Well, when you're doing this revision session, complete this work on a piece of paper and divide this piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this section write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure you write out your answers in full sentences and show your full working out, whilst on the right hand side write down any piece of information which you find useful or any hints and tips on answering questions from this revision session, and at the end of the revision session write up these notes into a revision sheet for you to use independently. So how should you be revising A-level physics? So first step is learn the key facts. So use your revision guides, class workbooks, student prep notes, textbooks to learn the key ideas of the course. Now to learn this knowledge you may wish to make mind maps or write out the notes yourself. You may want to then after this test yourself by using Caboodle, Seneca, your own knowledge checkers to quickly test your own knowledge, and you may wish to do this retrieval process from your own cue cards. Then the final step is practice and examination questions. So to do this practice you use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work, and you may wish to download your own past papers to do this. So the steps of learn the key facts, testing yourself and practicing exam style questions are what you should be doing to revise in A-level physics. So what are we going to cover in this revision session? Well, we're going to be looking at electromagnetic radiation and quantum theory, which includes the photoelectric effect, collisions of electrons with atoms, energy levels and photon emission, and finally wave-particle duality. So let's have a look at some multiple choice questions for electromagnetic radiation. So some energy levels of a lithium atom are shown below. A free electron with a kinetic energy of 6 times 10 to the minus 19 collides with a stationary lithium atom in its n equals 1 energy level. The lithium atom is excited to the n equals 2 energy level. What is the kinetic energy of the free electron after the collision? So pause the video now, then unpause the video when you want to go through your answer. Well, for this question the answer is A, because during excitation due to a collision with a free electron, the atom receives the energy equal to the energy level difference, which is from 8.6 times 10 to the minus 19 to 2.9 times 10 to the minus 19, so it's 5.7 times 10 to the minus 19. So if the electron had a kinetic energy of 6 times 10 to the minus 19 and lost 5.7 times 10 to the minus 19, you're left with 0.3 times 10 to the minus 19. The next question says, this graph shows how the maximum kinetic energy of photoelectrons emitted from a metal surface varies with the frequency of instant radiation. Which graph shows the variation of EK max with F for a metal with a greater work function? So pause the video now, then unpause the video when you want to go through your answers. Well, the answer for this one is C, because in the graph of kinetic energy against frequency, we know that the gradient of the line is Planck's constant, so the gradient has to remain the same as the graph given in the question, but the y-intercept is the negative work function. So if we've got a greater work function, we're going to have a more negative y-intercept. So you've got to choose a graph which has the same gradient as the one given in the question, but a more negative y-intercept. So that answer is C. The next question says a particle has a kinetic energy of Ek and a de Broglie wavelength of lambda. So what's the de Broglie wavelength when the particle has a kinetic energy of 4 Ek? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer here is A, because if the kinetic energy is increased by a factor of 4, then the velocity is increased by a factor of 2, because kinetic energy is proportional to velocity squared, so 2 squared equals 4. So if the velocity is increased by a factor of 2, then the de Broglie wavelength has decreased by a factor of 2, because lambda is equal to h over mv. The next question says evidence of the wave-like properties of an electron is what? So pause the video now, then unpause the video when you want to go through your answer. Well, the answer for this one is C, diffraction, because the emission of electrons from when light hits a surface, the photoelectric effect, the movement of electrons in a current, and the annihilation of an electron with a positron is all particle behaviour, whilst diffraction is a wave behaviour. The next question says, this diagram shows the energy levels in an atom drawn to scale. The transition from E4 to E2 caused the emission of a photon of green light. Which transition could cause the emission of a photon of red light? So pause the video now, then unpause the video when you want to go through your answer. Well, the answer for this one is C, because a photon of red light will have a shorter transition than that of green light, because red light contains less energy as it has a greater wavelength and therefore lower frequency, so therefore the transition of energy levels needed to cause this is going to be smaller than that for green. So the only one which is the case which is a smaller transition than E4 to E2 is in fact E3 to E2. The next question says, the graph shows how the maximum kinetic energy of photoelectrons emitted from a metal surface varies with the reciprocal of wavelength lambda of the incident radiation. What is the gradient of this graph? So pause the video now, then unpause the video when you want to go through your answer. Well, the answer for this one is going to be C. Why is the answer going to be C? Well, we know that the gradient of the line is the change in y over the change in x, so therefore it's ek over 1 over lambda, which is ek lambda. Then that's equal to hc, because you know E equals hc over lambda. That's an equation we were given, so therefore we can say hc is E times by lambda, so that's what the gradient is equal to. So the answer is C. The next question says, an atom in the inner coating of a fluorescent tube absorbs a photon of ultraviolet radiation. This causes excitation of the atom from its ground state. A photon of visible light is then emitted. Which energy level diagram represents this process? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer here is going to be D, because excitation only occurs with the absorption of one photon, because that's what's stated in the question. So there can only be one transition upwards to cause this excitation. But the emission of a photon occurs with a smaller transition than the excitation, because it's a visible photon produced, which has less energy than a UV photon, because it's got a longer wavelength, so therefore shorter frequency, so the transition downwards has to be a smaller difference than the transition upwards. So the only possible combination of this is D. The next question says, which role links both the photoelectric effect and electron diffraction to the properties of waves and particles? So pause the video now, then unpause the video when you want to go through your answer. Well, in this answer, the answer is C, because the photoelectric effect is a particle property and diffraction is a wave property. Those are just facts you've got to remember. So let's have a look now at a few longer questions. So the question says here, line emission spectra of hydrogen and antihydrogen have been compared. Explain in terms of energy changes how the line emission spectra are produced. So pause the video now, then unpause the video when you want to go through your answer. So it's important that you can explain how we get emission spectra and absorption spectra, which link into the energy level differences found inside an atom. So what you would say is that all atoms have energy levels which are discrete, so therefore emitted photon energy is going to be discrete values. So you know that emission is going to be produced when electrons are moved from a higher energy level to a lower energy level. Remember, absorption is higher is lower to higher, and emission is higher to lower. So therefore we know that the difference between the two energy levels is going to link into the energy of the photon, which then links into the wavelength and frequency of the photon, which is given in your spectra. The next question says, figure 3 shows some energy levels for a hydrogen atom. An excited hydrogen can emit photons of certain discrete frequencies. 3 possible transitions are shown. So these results in photons being emitted in the ultraviolet, visible and infrared spectrums of the electromagnetic spectrum. To which region of the spectrum do the emitted photons belong? So pause the video now, then unpause the video when you want to go through your answer. Well, it's important that you can remember the different comparisons in energy of ultraviolet, visible and infrared. Now, ultraviolet has the shortest wavelength and longest frequency, so therefore has the highest energy, and the infrared has the longest wavelength and shortest frequency, so has the smallest amount of energy. So this tells us the ultraviolet must have the biggest transition, infrared must have the smallest transition, and therefore visible must be in the medium. So we can see that it's C for ultraviolet, B for visible and A for infrared. The next question says, two ways to excite a hydrogen atom are by a collision with a free electron or the absorption of a photon. Explain why, for a particular transition, the photon must have the exact amount of energy, whereas the free electron only needs a minimum amount of kinetic energy. Then the surface of a sample of cesium is exposed to photons emitted in each of the three transitions as shown. The threshold frequency of cesium is 5.1 times 10 to the 14 Hz. Determine whether any of these transitions will produce photons that will cause electrons to be emitted from the surface of cesium. So pause the video now, then unpause the video when you want to go through your answers. Right, so this one you've got to understand that there's two types of excitation. Now the idea is that they can both be caused, it can be caused by either a photon being absorbed by the atom or a free electron colliding with the atom. Now both will cause the electrons to move to higher energy levels. Now because the photon is a particle of energy, all of the energy needs to be absorbed or none of it absorbed at all, because that's what the photon is, because the photon will only interact on a one-to-one interaction. So an electron, because it's a massive particle and not a particle of energy, can transfer some of its energy and keep the remainder of it. So that you've got to know that for photon absorption to cause excitation, it's got to be the exact energy level difference, whilst if you've got an electron, as long as it has that amount of energy, and then there could be some in surplus, it can cause that excitation, because it'll continue to move with the lower amount of kinetic energy if it's given some away for excitation. Now for the next question, what you've got to do is you've got to work out what the work function is going to be from cesium based on the threshold frequency and compare it to the transition to see if any of them would cause electrons to be emitted, because the energy of the transition is going to be greater than the work function. Now you don't have to do all three, because you know that C, because it's the biggest difference, is going to have the biggest energy for the photon, because the photon energy is equivalent to the difference between the two energy levels. So that's the most likely one that's going to cause excitation. Emission of the photoelectron. Now, how would you work that through? So you do work function equals Planck's constant times by the threshold frequency, and you work out the value in joules. You can then divide that by 1.6 times 10 to the minus 19 to get your answer in EV, and you see that it's 2.1 EV. You then look to the energy level differences in the atom, and you'll notice that C has a greater energy level difference than 2.1 EV, indicating that the photon produced in the transition of C from 2 to 1 will cause emission in the photoelectric effect. The next question says, photons each with 12.1 eV are incident on the surface of the cesium sample. Calculate the maximum speed of the electrons emitted from cesium. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, what you're going to have to do is understand that the total energy supplied by the photon, HF, is going to equal the work function plus the maximum kinetic energy. So what we do is we work out what the kinetic energy is by doing the total energy of the photon minus the work function. So we know that the work function is 2.1 eV from the previous question, and we know that the photon energy is 12.1 eV. So we find the difference of that and then multiply by 1.6 times 10 to the minus 19 to convert our EV into joules, because we want to work out a value for velocity in SI units or SI base units. So therefore we want to make sure that we're not using EV, but in fact we're using joules. We can then substitute that value of 1.6 times 10 to the minus 18 joules into the equation of half mv squared. We know the mass of an electron because it's given to us in the equation book. It is going to be 9.11 times 10 to the minus 31. We can rearrange the equation and work out V to be 1.9 times 10 to the 6 meters per second. The next question says, in a discharge tube, a high potential difference is applied to hydrogen gas contained in the tube. This causes hydrogen gas to emit light that can be used to produce the visible line spectrum. The visible line spectrum in figure 8 has been used to predict some of the electron energy levels in a hydrogen atom. The energy levels predicted from the visible line spectrum are those between 0 and minus 3.40 EV in the energy level diagram. So calculate the energy in EV of a photon of light that has the lowest frequency in the visible hydrogen spectrum shown in figure 8, and then identify the state of an electron in the energy level label 0. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, the first thing you've got to do is identify where you're going to get the lowest frequency. Well, the lowest frequency is going to be given on your spectrum by the longest wavelength, because the higher the wavelength, the lower the frequency. So we identify that our wavelength we're going to use is 656 nanometers. We can then say E equals hc over lambda. We know h, we know c, we've got worked out what lambda is, and then we're going to work out what E is then. So we work out E to be 3 times 10 to the minus 19 joules. We can then convert that into EV, because we know that we want the answer in EV for this question. So to convert to joules, we divide by 1.6 times 10 to the minus 19 joules to get it into EV, so it's 1.9 EV. Now when an electron is labelled as 0, we know it's out of the potential well that it's in. So therefore the electrons are free. They're no longer bound to the atom. The next question says, identify the state of an electron that is in the energy level labelled minus 13.6 eV and explain why energy levels are negative. So pause the video now, then unpause the video when you want to go through your answer. Well, it's very important that you note that the minus 13.6 eV is the value at the lowest point of this particular energy level. So we call those the energy levels closest to the atom. The lowest value is going to be the ground state, the lowest level an electron can occupy. Now, why are energy levels negative? Well, it's important that to become free or to be set away from the atom, the electron is given an energy of 0, because it's no longer bound to the atom. So if we've got to put energy in to get to 0, it must be starting as a negative number, which indicates why all electron energy levels are given as negative values. The next question says, discuss how the discharge tube is made to emit electromagnetic radiation of specific frequencies. In your answer, you should explain why there must be a high potential difference across the tube. Discuss how the energy level diagram in figure 9 predicts the spectrum shown in figure 8, and show how one of the wavelengths of light is related to 2 of the energy levels in the energy level diagram. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you should be doing for these types of questions is answering every single bullet point one by one. So why do you need a high potential difference in the tube? Well, the high potential difference will accelerate electrons, so when they collide with the electrons the atoms in the atoms in the tube will then be excited, so therefore the electrons inside the atoms of the tube are going to go to higher energy levels. So the next point is asking, what's the relationship between the spectrum and the energy level diagram? So what you would say is, because it is an emission diagram, you would say that the electrons in the atom are going to de-excite, and when they de-excite, okay, they will move to lower energy levels, and therefore it will result in a photon of radiation being produced. The energy of this photon is going to be the difference of the 2 energy levels, and therefore you can link that into the wavelength by saying E, the energy, which is the difference of the 2 levels, is equal to hc over lambda. And then what you do for the final mark is then work out a value of lambda by looking at your energy level differences, saying working out the value of E in EV, convert that into joules by times it by 1.6 times 10 to the minus 19, the conversion factor, then say E equals hc over lambda, to say lambda equals hc over E, pop the numbers in, and you should get a value for lambda which is equivalent to one of the values in the energy level spectrum diagram. The next question says, figure 1 shows an arrangement used to investigate the photoelectric effect. A current is measured on the microammeter only when electromagnetic radiation with a frequency greater than a certain value is incident on the photoemissive surface. Explain why the frequency of the electromagnetic radiation must be greater than a certain value. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this type of question? Well, you'd indicate that frequency links to the energy of the photon, which is absorbed, which is going to be absorbed by the metal surface, and the idea is that E is equal to hf. So therefore you'd have to have a minimum energy of a photon required to move a photoelectron, which links into the minimum frequency of that, because the idea would be that you've got to have a work function to overcome to release that electron via the photoelectric effect. So therefore the energy of the photon has to be at least that value, okay, or above. The next question says the investigation is repeated with a different photoemitter surface that has a smaller value of the work function. The source of electromagnetic radiation is unchanged. Describe the effect that this change in the surface has on the value of the stopping potential. So pause the video now, then unpause the video when you want to go through your answer. Well, what you've got to remember is that stopping potential links into the electrical potential energy, which is equivalent to the kinetic energy of the photoelectron. And we then also know that the total energy of the photon is split between the work function and the kinetic energy of the emitted photoelectron. So if the work function is less, that tells us that more of the energy of the photon is going to the kinetic energy of the emitted photoelectron. So therefore, as the kinetic energy is higher for the emitted photoelectron, you will need to have a greater stopping potential to stop that electron from moving and convert that kinetic energy into electrical potential energy. So I hope you've enjoyed this particular revision session on electromagnetic radiation. So hopefully, if you've been successful and learned in today's lesson, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics. So thank you very much for watching this revision session on electromagnetic radiation. Thank you very much and have a lovely day.